This is a lesson on elastic collisions in the calculus-based mechanics unit. I wanted to review a few things here before I moved into elastic collisions. Conservation of linear momentum. We're working with well-defined objects and that have well-defined masses and well-defined velocities. And in order to do conservation of linear momentum, we need to establish that the external force on the system of objects is zero. There's no friction acting over the course of the collision, no net external force. And so if the external force is zero, then overall the impulse is zero and the change in momentum is zero. And if the change in momentum is zero, then we have conservation of momentum. The initial equals the final. And I'm going to remind you that I can do this in the x dimension separate than in the y dimension, and that allows me to do momentum conservation in multiple dimensions separately. Remember, this is a vector quantity, and we can decompose the momentum into x, y, z components if we need to, and that's conservation of momentum. And in a prior lesson also, I talked about the different types of collisions. So the difference between an elastic collision, where we have no loss of energy, and an inelastic collision, where there's some sort of energy lost, and the only form that we're looking at for energy lost is kinetic energy. The energy goes into sound or deformation, friction, etc. But that's an inelastic collision. I'm going to remind you that inelastic collisions doesn't necessarily mean they stick together. It's just that there's some sort of energy loss someplace. So even when you just bounce a ball on the ground, it may seem like it's elastic because they don't stick together. But when you bounce a ball on the ground, it doesn't return to the same height as it started at, and that's how you can tell that there was some energy lost, even though the objects don't stick together. So don't assume because two objects stick together you have an elastic collision. It has to be very specifically defined as an elastic collision. I'm also going to remind you our different forms of kinetic energy. We may need this as we move into elastic collisions. Since kinetic energy is conserved, we could use different forms of kinetic energy in order to find the different quantities. It depends on the information given in the problem. For this situation, I chose a very simple problem for us to practice what the center of mass. We're moving into and this is why I'm bringing it up. We're going to use the center of mass velocity in order to solve elastic collisions. And you'll see why in a second. But I wanted to remind you of the center of mass velocity, how to calculate it if we have multiple objects. Typically in a collision, we'll have only two objects. So we'll just use two weighted terms here in order to find that average velocity for the system. So what we're going to do is with elastic collision, there's an interesting fact that is true about collisions is that in the center of mass frame, when I look at the center of mass frame, the velocity of the incoming objects, the incoming velocity for the objects for the collision is going to be the same speed as the outgoing. So that's why I have drawn here or these diagrams. Let's talk about it for a second. So let's say I have two blocks heading toward each other with some sort of initial speed, and we're looking in the ground frame. Over here is the ground frame. And so what I have is block B. Actually, I have block B, if you notice, from the first frame to the second frame, or first picture to the second picture. Here's the initial situation is A is heading towards B and B is just sitting still. And A hits B. When I look at this, let's assume they're the same mass. The center of mass is in between, right? There's the center of mass. And then when they hit each other, the center of mass is still between them. And when they start moving, A is going to have some sort of final velocity and B is moving after the collision as well. And you can see that the center of mass is moving, right? Here the center of mass is moving in the ground frame. which is what we normally experience in the everyday world is the ground frame. But in order to use this fact that I've stated up here, we're going to shift to the center of mass frame. All right. So in the center of mass frame, the center of mass is going to stay in the same location, right? In the ground frame, the center of mass moves. But in the center of mass frame, the center of mass is at rest with respect to itself. So the center of mass is here, the center of mass is here, the center of mass is here. It stays in the same location as the collision occurs. So in the center of mass frame, I have A has its initial speed, but in the center of mass frame, B is also moving in the center of mass frame. All right. Before the collision, so we call this VA initial star, and this is VA initial. So that's how we denote the different speeds in the different frames, is that there's no star for the ground frame, but when we go to the center of mass frame, we're going to put a little star on top, and you can see that down at the bottom here. I used an asterisk. So VA initial and VB initial, and they both have stars on them. In the collision, A and B collide here, and then afterwards you can see that they're going to, which is what the fact is down here, whatever the initial velocity is, the final velocity is just going to be the negative of it. So VA final star equals negative VA initial star. Okay, so whatever this incoming velocity was in the beginning, it's going to be equal but in opposite direction. And I'm going to say the same thing about B as well. It had incoming velocity in the center of mass frame. It's going to have the same but negative outgoing velocity. Okay, so that is the convenient fact that we're going to use in problem solving. But what we need to do, and you're noticing here, is that we have to transfer from the ground frame to the center of mass frame. So that's going to take a step in our problem solving in order to get from the center of mass frame, from the ground frame to the center of mass frame, do the collision in the center of mass frame, and then convert back to the ground frame. So I've summarized the problem solving steps in this slide. You can take these to the bank. This will be the same every time you do an elastic collision. You can do it in the center of mass frame. So solving collisions, solving elastic collisions in the center of mass frame. So here's our center of mass velocity. In order to move to the center of mass frame, we need to know what the center of mass velocity is. And like I said, we're going to use just typically two objects, and we know how to use that formula from a prior lesson. Once we have the center of mass velocity, we're going to convert the initial velocity for each object into the center of mass frame. So we're going to go from the non-star initial velocity to the star initial velocity by just subtracting v center of mass. That's all you have to do is subtract the center of mass velocity. Pretty easy. Seems pretty easy. Now that we're in the center of mass frame, we have v initial star. Well, we can use our negative relationship. V final star is negative V initial star. That's an easy step too. Whatever number we get into, we're going to take the negative of. And then once we have that final velocity, we're going to convert it back to the ground frame by undoing what we did in step 2. Notice in step 2, we subtracted the V center of mass. Now we're going to add V center of mass back on in order to get the final velocity in the ground frame. So you'll need to put these to, typically these steps are not on an equation sheet. You'll need to put them to memory. Okay. And so that's why I outlined it as logically as I did, to make sense of why we're doing this process, is to use the fact V final star is negative V initial star. We have to have it in the center of mass frame. And if we want it in the center of mass frame, we have to know V center of mass. V center of mass, subtract it off, take the negative, add V center of mass back on. Okay, so I've chosen one problem for us to do today, and it's conveniently only in one dimension, so you can see how this works. Let's see. It looks like a lab sort of situation where we have two carts banging into one another. 493 gram cart traveling at 6.5 meters per second collides elastically. So we're seeing that in there. We need to see this word elastic in order to use this strategy. Collides elastically with a 709 gram cart traveling at negative 6.5 meters per second. Determine the final velocity of each cart after the collision. Notice that we do not have enough information to do this in the lab frame. Or I guess we could, if we wanted to set it up, you'd have M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. Okay, so we have two unknowns in this one momentum equation. The other equation you could set up here is conservation of energy, right? Change in kinetic energy for this collision is 0. So you could set up the 1/2 mv1 initial squared plus 1/2 mv initial 2 squared equals m1, right? So forth. And so you're solving a quadratic equation with two, it's nonlinear system of equations. It becomes a little bulky with the algebra. So instead of doing this method where we have two equations, two unknowns, we're going to use this strategy of elegantly just doing the negative of the velocity in the center of mass frame. So let's do this. Calculate the center of mass velocity. I can do this. The M1 is 493 and it's moving in the positive direction at 6.5. I'm going to add on the second mass, 709 grams at negative 6.5. I'm going to note you could convert this to kilograms, but if I keep it in grams and I divide by grams, overall the grams will cancel on top and bottom and I'm left with meters per second. And when you multiply by this through, the 709 is obviously the larger cart, and so the center of mass velocity is going to be in the negative direction, 1.168 meters per second. Okay, so I can deal with that. That makes sense. I have my center of mass velocity. Now, our second step says convert the initial velocity for each object to the center of mass frame. So I need to do this for both objects. So V A initial star, right? I have two carts here. I'm going to call the small cart A and the big cart B. I hope that makes sense to you. V A initial star is going to equal V A initial minus V center mass. So I'm going to go 6.5 minus negative 1.168. Okay, and you can see that I've got a double negative here. I'm going to end up adding them together, so that's 7.668 meters per second. Okay, let's do the same for B. VB initial star equals VB initial minus V center mass. So I'm going to have a negative 6.5. I like that that's the same value, just different directions, minus the negative 1.168. So I'm going to take negative 6.5 and add on 1.168, and this becomes negative 5.332 meters per second. Okay, so that's V initial star for each object. Let's find their final velocity. V final for A star equals negative VA initial star. So I'm going to take the negative of 7.668. So that's a positive 7.668. Sorry. It is not a positive. It is definitely a negative. The negative of a positive is a negative. So that makes sense to me. When these two hit each other, if A is moving in the positive direction before the collision and it's an elastic collision, it's going to bounce back in the other direction, right? VB final star is going to be negative VB initial star. So I'm going to do the negative of negative 5.332. Okay, so this makes sense as well. B changes direction to the positive 5.332 meters per second. It bounces back in the positive direction. So let's undo. Let's get back into the ground frame. We're going to undo in this step what we did in step 2. So we're going to add back on the V center of mass. So VA final equals VA final star plus V center of mass. Okay, so I'm going to take VA final star, negative 7.668, and I'm going to add on negative 1.168. So overall, it's going to have a large velocity in the negative direction, negative 8.836 meters per second. And I expected this. We had a small cart and we had a big cart, and when it rebounds in the opposite direction, VA final, it's going to have a large velocity here. That's what, or large speed. That's what it's saying. VB final, let's find VB final is VB final star plus V center of mass. So I'm going to take positive 5.332. I'm going to add on the negative 1.168, and it's going to end up moving in the positive direction after the collision. It's bigger, so it's going to have a proportional momentum, but its speed is going to be smaller in order to plus 4.164 meters per second. It's going to have a smaller velocity in order to balance out. So it bounces off into the positive direction, VB final. Okay, so that's how you use that 4-step method, that 4-step strategy in order to do elastic collision in the center of mass frame. And like I said, usually you have to remember these steps. So hopefully it makes sense why we do each step. It's not just a rote memory thing, but each step makes sense why you're doing it, and that will help you remember the strategy.